Sir, should I disable the waiting room, sir?
Yeah, disable that. Right. So look at here, as we learn in the gravitation concept, this gravitation concept, first one is Kepler's laws, right? In this gravitation, we learn about the first one is Kepler's laws. Kepler's totally proposed three laws. First one is law of orbit, law of area, law of time period. And after that, I give a relation between F and G. So according to the Newton, any of the two objects, it shows some attraction and repulsion force. So force is directly proportional to product of their masses and inversely proportional to square of the distance. So when you are adding these two, you are going to get F equal to R square. So F equal to G capital M small m by R square. G is universal gravitational constant. The value of universal gravitational constant is 6.67 into 10 power minus 11 Newton meter square by kilogram square. Right? Then how we are going to get this value? On which experiment? What is the experiment name?
Cavendish
Yeah,
experiment.
Cavendish experiment. So when you suspended a rod to two spheres, like a big spheres, now you are going to be observed. Now, like the suspension, this is a big sphere we added from here. Now we are keeping a small sphere. Now, not in the instant time. Now it takes so much time. Now it is going to be attract. Some rotation you are going to be observed, right? From the based upon that one, where it is rotated, it experiences by force. That force we are taking as a torque. So torque tau b equal to, you can write a force into perpendicular distance. So tau equal to G mm by R square into d theta. So when you are simplifying that, you will get G value nearly 6.67 into 10 power minus 11 Newton meter square by kilogram square. What is the dimensional formula? Fast. G dimensional formula. Anyone? What is force dimensions? ml t power minus 2. R dimensions L. By mass is m square. So you will get m equal to 1 minus 2 become minus 1. M power minus 1, L power 3, T power minus 1.
L power 3 power minus.
M power minus 1, L power 3, T power minus 2. This is dimensional formula for universal gravitational constant. So after that, we learn about gravitational potential energy. So the gravitational potential energy also, we are keeping the two objects. This object is coming from at infinity to a particular point. That point is R. So in that situation, we got gravitational potential energy U equal to minus G capital M small m by R. Just R only. Remember this equation, I'm going to ask you again. Minus G capital M small m by R. After this, we learn one more concept. What is that concept?
Altitude.
Yeah, altitude. So in that altitude, what did you found last equation? So what is our aim or why we are finding that altitude? Why we are finding that altitude? So here, this is the Earth's surface. This is the radius R. And here the object. We are lifting the object at particular height. So this is the height h. Total distance is R plus h. Right? So as you know, the relation between small g and capital G. What is the relation between small g and capital G?
G R
R square
G
is equal to
capital M.
GM.
Small g equal to capital GM by R square. So GM equal to GR square. Remember this part, right? Now coming to here, here we have the total distance is r plus h. This is capital M mass. This is small m mass. So using Newton's laws, we can write F equal to capital G, capital M, small m by, what are you going to write?
R plus H whole square.
Very good. R plus H whole square. So F equal to, mg. Mass into acceleration due to gravity at certain height h equal to G capital M small m by R plus H whole square. Small m get cancelled. So acceleration due to gravity at certain height h equal to G capital M by R plus H. So here, according to this relation, small g and capital G, instead of gm, we can able to write gr square. So gh height equal to gr square by r plus h whole square, right? So we need to take the common term here. So when you are taking the common term, gh equal to gr square. Now I'm taking the common term. This is the whole square. R is the common term. So what you will get left of the term?
1 plus
One
h by
plus
r.
h.
H by R, not only 1 plus H. If you're writing only 1 plus H, you won't be get exact equation, even though that mathematical part is wrong. So 1 into R become R, R into H by R get cancelled, you will get H. So GH equal to GR square divided by R whole square into 1 plus H by R whole square. So R square get cancelled. So GH equal to G into 1 plus H by R whole square, whole power minus 2.
Minus 2.
So when you are applying the binomial expansion, you will get the final equation GH equal to G into 1 minus 2H by R. 1 minus 2H by R. Is it clear? Do you have any doubts? This is the acceleration due to gravity when the object is moving at certain height, altitude. Is it clear? Any doubts? Anywhere you have any doubt? Is it clear?
Yes, sir.
Now depth. Now acceleration due to gravity is going to be decrease or increase when the object is moving inside the Earth's surface. When the object is moving inside
Increase,
the
sir.
Earth's surface, it increases. Yeah, let me see if it is going to be increase or decrease. Now, I'm taking, here the object is there. From center to this part, this is the Earth's surface. What do you call this?
Radius.
Radius, capital R. So this object I'm bringing at certain depth D. Here we have the object. So how much distance from here to here? Sorry, from here to here.
R minus D.
R minus D. Good. So what you are supposed to write is consider on the Earth's surface any object, its mass is small m. Earth surface, so Earth mass is capital M, it is having the radius R. The object is moving inside the Earth's surface, means at certain depth D. So the remaining distance is R minus D. As we know, small g equal to gm by R square, right? This is the depth. GD equal to gm by R square. Now I'm writing the relation, density relation. What is the formula for density? Anyone? Density, ma. Density rho equal to really don't know formula for density?
Mass by volume.
Good. Density rho equal to mass by volume. What is unit of density here? Density units, kilogram per meter cube. So you can write mass equal to density into volume. See here, the Earth's surface we are considering as a sphere. Volume of the sphere formula? Volume of the sphere. Right? 4 by 3 pi r cube. 4 by 3 pi r cube. So this m is I'm substituting here. G equal to G by r square into mass 4 by 3 rho pi r power 3. So square, this cube get cancelled. So what you are going to be get the final equation? G equal to 4 by 3 capital G rho pi r. Is it clear? So G equal to 4 by 3, sorry, small g equal to 4 by 3 G rho pi r. So it's the object is moving inside at certain depth. When it is moving the depth d, so the distance become r minus t. Now I'm writing that one also. Depth d equal to 4 by 3 g rho pi r minus d. You can take equation 2 and equation 1. Now dividing equation 2 by equation 1. 2 by 1. GD by G equal to 4 by 3 pi capital G rho pi into r minus t whole divided by 4 by 3 pi 0 pi r. So G depth by G equal to r minus d by r. So GD equal to I'm sending this part this side. G into r by r minus d by r. R get cancelled. So G depth equal to G into 1 minus d by r. This is the final equation. This is the depth acceleration due to gravity. G into 1 minus d by r. Now, what do you got the previous equation? Height value. Tell the formula for height. GH equal to G into? Tell.
Sir, G into 1 minus H by R.
H by 1 minus H.
1 minus H by R.
Paka, right? Little mistake is there. 1 minus 2H by R.
2H by R, sir.
Right? So we have one MSET question. That's the reason I asked you. So when height and depth are equal, what you will get H value. So H in terms of depth you are supposed to write. Just equate these two. So when you are equating this one, GG get cancelled. 1 minus 2H by R equal to 1 minus D by R. Here 1 also get cancelled. Minus also get cancelled. RR also get cancelled. So 2H equal to D, then H equal to D by 2. Right? Sometimes it's going to be asked like that. So up to here, IP1. Is it clear up to here?
Yes, sir.
Depth.
Yes, sir.
Right. Next, we are entering into orbital velocity and escape velocity. Right. So orbital velocity. So when I was asking the orbital velocity, just you can imagine we are sending the satellites. So these satellites, it is entering into where? In universe. The universe, right?
Yes, sir.
Enter into one orbit. So in that orbit, it is going to be enter. Or suppose one orbit to another orbit. It need to be jump from one orbit to another orbit. It need to be we need to apply more energy or less energy. It want to jump from one orbit to another orbit.
More
so
energy.
to apply more energy. So here also orbital velocity. First we learn about orbital velocity. So in this orbital velocity, as you know, first suppose imagine one planet, sun is at the center, all the planets is revolving. It's revolving with how much velocity? That's my question. So fine, here sun is at the center, all the planets is revolving this way of direction, right? So whenever force is acting, what is that force? One of the force is pulling inside. What is that force?
Centrifugal force.
Right. What is the formula for that? What is the formula, ma? Centripetal force. Yesterday also we did a problem. F equal to? Yes, right. F equal to mv squared by r. So coming to here, before that we are applying the centripetal force. Now, as usual, we are considering. First, we need to learn about orbital velocity definition. Very easy. The horizontal velocity required for an object revolving in a circular orbit. The horizontal velocity required for an object to revolve in a circular orbit is called orbital velocity. Anyone give the definition? Again, the horizontal velocity required for an object to revolve in a circular orbit, right? Is it clear? Is it clear definition?
Yes, sir. Yes, sir.
Yeah. After that, this concept, we have escape velocity is there. Escape velocity definition, the minimum velocity required for an object, escape from the gravitational influence. Escape from the gravitational influence. So for suppose if you are throwing a stone, like normal energy, if you are applying, it will be come back. But if you are applying more than orbital velocity, it won't be come back. So how much velocity you need to apply, I'm going to tell you. So coming to here, this is one orbit. This is the orbit. It's a planet is revolving this way of direction. Like this is the sun, one orbit. This is capital M, this is small m. According to, you can take this is R. According to Newton's laws, you can write F equal to G capital M small m by R square. Right? So F is centripetal force, as you told, mv square by R equal to G capital M small m by R. So this I'm going to be get cancelled. Square R get cancelled. This is orbital velocity. V r equal to G capital M. So instead of Gm, what you can write, ma? Instead of Gm, what you can write? According to small g capital G relation.
GR square.
So V not equal to root over Gm. We know GR square equal to G capital M. This is the relation. So V naught equal to root over GR square by R. R square get cancelled. So you may get orbital velocity formula root GR. So V naught equal to root over G value 9.8. R value, what is the radius of orbit? So radius of Earth. Acceleration to gravity, G value I put 9.8. Then what about R value? Yesterday only given radius of the Earth.
6,700.
6,400 kilometers, converting into meters, 10 power 3. So orbital velocity you will get 7.92 kilometer per second. 7.92 kilometer per second. So one thing I would like to give the conclusion for you. Just here, this is the radius of the Earth, right? We are sending a planet at certain height, so it is revolving like this. So this is the height h. The total height is r plus h. So you can write here r plus h whole square. R plus h whole square. Here also you can take r plus h. Square get cancelled. So r plus h. Here r plus h you can take R is greater than H. So H is going to be neglected. You will get R only. So finally, you will get 7.92, right? Orbital velocity. The orbital velocity, again, I'm going to explain it because that will. So orbital velocity means the horizontal velocity required for an object revolving in a circular orbit. So from Earth's surface to we are sending one satellite. It is entered into a orbit. So Earth radius is R, at certain height is H. Total distance is R plus H. Set value of force, you can write mv square by R. This is orbit. R is, you can write R plus H equal to G capital M small m by R plus H whole square. Square, this get cancelled. Get cancelled. So V naught square equal to G R square by R. So we are taking R is greater than H. So H is going to be neglected. So V naught equal to root GR. So G value 9.8 and R value 6400 into 10 power. So what is the value I told you just now? How much? Orbital velocity.
7.92 kilometer per second.
Yeah, 7.92. This is orbital velocity. So any of the orbit, it need to be revolved in a circular orbit. It need to be maintained 7.92. Now I'm asking you escape velocity. So for suppose it need to be escaped from this Earth surface or from that orbit. It need to be changed from one orbit to another orbit. It need to be applied 7.9 or 7.6 or 7.7. Which one? It need to be escaped from the orbit. Its speed will be less or more. It want to escape from that place.
Less, sir.
Why less?
Because it requires minimum velocity, no, sir.
So, for suppose this part, this is the planet, this is orbit, this is another orbit. So here the object is moving like 7.92. It need to jump from here to here. It need to be applied more or less?
More.
More. Comparing to 7.92, we need to apply more. Best example, here one thief is there. The police is catching the person. He is near to this person. He is running this way. So this police is coming near to this way. Just like 2 meters only is there. He use his energy will be more or less. He want to escape from police. He will use more or less.
More energy.
More
energy.
sir.
Even police also apply more energy, right? Same thing here also. It need to be escaped from that orbit, from one orbit to another orbit. So we will get the value, how much nearly I would like to tell you on deriving the equation you will get. So what did I told you just now? Escape velocity definition. Just now I told you now. Escape velocity.
The minimum velocity required for an object to escape from the gravitational force.
Influence. Very good. The minimum velocity required for an object escape from the gravitational influence. That is nothing but escape velocity. So in this escape velocity, so it has some energy, like some potential energy. It is coming from somewhere like natural or somewhere. So it need to be escaped from this. No, it has some energy. It need to be at more energy. Means total energy become constant. So I'm telling that the total energy is nothing but sum of kinetic energy plus potential energy. So this is become 0. You can write kinetic energy equal to minus potential energy. So what is the formula for kinetic energy? Half
mv
square. This is escape. So minus of, as I wrote here, gravitation potential energy. What is the formula? Minus G capital M small m by R. You can write R plus H So R is greater than H. H is neglecting. So minus into minus plus. Half mv square equal to G capital M small m by R. This get cancelled. V square by 2 equal to Gm by R. So you can write here V E square equal to 2 Gm by R. So instead of Gm, what you can write?
GR square.
That's
GR square. Very good. So V square equal to 2 into GR square by R. This get cancelled. So V equal to root 2GR. So V equal to root over 2 into 9.8 into 6400 into 10 power 3. So escape velocity is 11.2 kilometer per second, right? So orbital velocity, I told you 7.92. Escape velocity we got 11.2. So comparing to orbital velocity, escape velocity is more or less?
More.
more, sir.
More.
More,
So if you want to write the relation between escape velocity and orbital velocity, so how much it is more comparing to escape and orbital velocity? So escape velocity we got root 2gr. Orbital velocity we got gr. So how much time it is more? Root 2 times more.
Root 2 times.
Yeah. This is root 2. This one also be one answered question. V equal to root 2 V naught. After that gravitational, we have this geostationary satellites. One more concept is there, that is geostationary satellite. So up to geostationary satellites in your quarterly portion. After that we have time period of satellite, that is not important, only for objective purpose I discussed, but I'm going to discuss in the tomorrow class. Now geostationary satellite. Why they kept the name of geostationary satellite? That is my question. Anyone tell? Geostationary satellite. Why they kept the name? Anyone? What is meant by geo? Not J-I-O, G-E-O. Tell what is meant by geo? Geographical. Okay, what is meant by stationary?
Fixed at a
Stationary.
place.
Yeah, fixed place. It is not movable. It's movable, but it's a fixed. Okay, stationary. It's a constant, right? Satellite. What we are sending to in a orbit, that is a satellite. Then geo means, if you know geo, you may get the answer.
For a particular geographical area.
Particular geographical area. No. No. See, geostationary satellite. See, we are sending a satellite to in your orbit. So when you are watching the satellite from the Earth's surface, so whenever you are seeing that satellite, it is in the state of rest. Why you are looking it is in the state of rest? What was the reason behind that? Can you tell? Even that satellite is revolving. How we are revolving in a orbit, same thing the satellites also be going to revolve. But whenever you are seeing that satellite, you feel that it is in the stationary. So that's the reason they kept geostationary satellite. When you are seeing from the Earth's surface only, it is in the stable, like it's stationary. Why? It is in state of rest.
Excuse me, sir.
What is the time period of Earth? Yeah, tell.
Sir, should I stop the recording?
Chitresh. Yeah, you can stop it and send to me.